Hello and welcome back. Today I'm showing you my new tube preamp, Electric Rain. I developed it based upon the Hughes Kettner Tubeman Mk1. But as it turns out, there isn't much left of the original circuit, and overall I gave it a lot more gain. You can see two independent channels and no switching noise whatsoever, speaking of physically, and in the speaker. It's absolutely dead quiet. And of course, if you want to build this device yourself, I'm sharing all my schematics with you. So if this sounds interesting, stay tuned. Okay, if you're interested in the circuit design and the schematics, this part is for you. Even though I really liked the Tubeman Mk1, there were some problems in the circuit and of course the obvious elephant in the room. No foot switchable channels, just a rotary switch. My design goals are the following. First, solving the oscillation problem in the original design. Then, model the sound exactly to my likings. And the design overall should be a preamp, not a simple distortion pedal. Those distortion pedals are some kind of a one-trick pony. It should do cleans as well as crunch, overdrive and metal distortion. Plus, I want to leave room for Tonestack modification afterwards. And of course it should be a 2-channel design with gain, volume and EQ section each. The channel switching must be noiseless, so no popping noise at all. And my last point, no microcontrollers should be involved. The whole circuit must be repairable, only off-the-shelf parts were used. So it's pretty obvious that I have to do a complete redesign. Sorry Hughes and Kettner, it is no longer a Tubeman. But wait, there is a Tubeman Mk1. It has 3 channels, which are foot switchable. Yeah, but I don't like the tone at all. Plus, the 3 channels are sharing the same EQ. This is pretty bad. But first things first, let's design a proper switching circuit. As said, no microcontrollers. I love them and I use them all the time. See my other videos in which I built a Geiger counter. But I want this device to be repairable. And this means I am going the traditional route. Yes, the NE555 will handle this job. I can be dead sure that this chip will be manufactured at least for some decades. Let's have a look at my prototype circuit. When it comes to more complex projects, I am splitting it into specific parts. Here I am triggering the channel switching, which is indicated by the bicolor LED. The red LED in the front view is indicating when the output signal is muted. This way, the popping noises introduced by the relays are no longer a problem. Let's discuss my attempt to this common switching problem by taking a look on my schematics. Of course, this can be solved in many different ways. This is my way. As told previously, the big problem when switching signals is that in general they are often on different voltage levels, and if you switch them, for example via relay, you can hear an annoying pop sound in the speaker. This can be solved by muting. So this circuit addresses 2 objectives. First, switching the channels and give some LED output. Second, while switching, muting the output signal by pulling it to ground. The idea of the operation is the fact that mechanical relays are switching much slower than the semiconductor, in this case a photomos. Therefore, the photomos mutes the signal before and while switching the relays and preventing this way from popping noise. Let's take a look at IC5. This must be a CMOS version. IC5 is for channel switching. IC6 on the other hand is for muting the signal while switching the channels and is triggered by the output of IC5. The trigger pin 2 of IC6 can't be driven by a constant voltage, because this would mute the signal constantly. Therefore a short pulse is necessary. This means pulling trigger pin of IC6 to ground. C42 and C40 is mandatory to block DC. But it doesn't stop here. C42 and C58 is stabilizing the trigger behavior of IC5 and is preventing from false trigger. C57 is stabilizing the trigger behavior of IC6 and is preventing also from false trigger. Last but not least, R66, C41 and finally C63 is forming the timing network. This must be adjusted for a specific mute time. The values I've given to you are working fine for me, but of course you can adjust them to your liking. For now, let's leave all this theoretical stuff behind and do some real work on the PCB which I designed. After soldering and testing, I am explaining the circuit and discuss some design decisions I made. And these are all the components for the preamp. I've already picked them out. But first I'm going to solder the power supply part of the circuit. Normally I would recommend to start soldering with the lowest or tiniest parts, like resistors or diodes. But when it comes to testing new builds, it is better to solder each section after another. This way you can test them separately, and in case something goes wrong, you can way better nail down the fault to a specific part or component. To this moment in time, while shooting this video, little I know that I will encounter exactly this. The power supply is ready for testing. Now I'm checking all the voltages. And we've got around 247 volts. That looks good. And the filament/heater supply voltage is at -16.7 volts. Don't get confused with this high or low value. I discussed this in a moment. But first I'll check the other voltages. This is the dual rail supply of the ICs to allow more headroom. There's a little voltage difference of 0.5 volts. This is not a problem. We have to keep in mind that there's no load at this point, and they will be slightly different later on. I designed the PCB for many different transformer options. This is why there are connector cables. This way I can choose almost any transformer with different pinouts as long as they have the same footprint. Let's have a look on the schematic of the power supply. The transformer is wired backwards, also called backfed, because 12 volts AC as a primary to 230 volts as a secondary, at least here in Germany, are very hard to find. With this method there are some things to keep in mind. All transformers have winding resistance that causes a voltage drop. A standard transformer has about a 3 to 5% voltage drop caused by winding resistance at full load. Transformer designers compensate the windings ratios to account for the voltage drop. When a transformer is backfed, the compensated winding ratio will work against the user. Not only does the 3 to 5% voltage drop occur, the compensated windings ratio also adds a 3 to 5% voltage drop. As a result, backfed transformers can have 6 to 10% voltage drop at full load. For this reason, it is necessary to use a 9 volt AC transformer to get the real 230 volts DC after rectification. Another downside is that the inrush current is higher. Since we are dealing with small currents, this is not a problem. And please notice, the heater supply is chosen to be negative to balance the load a bit. The goal is to have nearly the same current draw on the positive rail as on the negative rail, since there are no dedicated voltage regulators for the -15, -12, +15 and +12 volts rails. If the heater supply would be positive too, the voltage would drop even more on those positive rails, which results in a bigger difference to the negative supply rail. Another approach would be to use a dedicated negative and positive linear voltage regulator, but this would add even more complexity to the circuit and the current draw would be much higher. And now back to my PCB. I populated the linear voltage regulator for the switching circuit. And what the... This doesn't look right. It should be 5 volt and this thing gets hot instantly. I can tell you this is the first time ever that a fresh part is broken. I mean, I store them properly in ESD bags and handle them, of course, with care. That's a dead shot, I guess. Let's compare to the new part. Yep, that's confirmed. After this repair job, the voltage is where it should be. Perfect. With the magic of video editing, the switching circuit is also ready for testing. Remember my prototype circuit in which I tested the switching function with an LED? This is exactly what I am doing right now. On the schematic you can see that I'm switching the test LED to ground. It is simulating my guitar output signal. Finally providing some power. And yes, it already works. But for further testing, I'm using a pair of pliers to act like a switch by shorting out the traces. Beautiful. And one last time switching back to the red channel. Often I read comments in forums and here on YouTube that circuits like these are no real tube preamps. Such blanket statements are highly problematic. It always depends on the individual circuit. If you put everything on the balance, almost no tube amplifier is authentic. This starts with the rectifier, the sagging effect. Very few amplifiers have rectifier tubes. When it comes to preamps, it depends on where the distortion mainly occurs. In this circuit, the main work is done by the tube. The ICs are mainly used for filtering and boosting the frequencies. When complaining about these ICs, keep in mind that an enormous number of preamps use ICs in this function. Mesa Boogie does this too. But back to the circuit. I use real high voltage on the tube here. I also put a selector switch on the board, which makes it possible to modify the Tonestack. The values I have chosen here are exemplary. I leave it in the default settings all the time. Other than that, there's nothing special in the main preamp circuit, but if you have any questions, feel free to ask. Off camera, I finished the soldering. But now I'm really curious what my prototype preamp looks with some thermal imaging. The temperature looks good, no problem so far with the linear regulator. Around 60 degrees Celsius is fine. Look at this tube. Now I'm drilling the chassis. By the way, the drilling template is also in the archive for download. Okay, in the following I'm noodling around with the Tonestack. If you're interested in what's coming up next on this channel, watch the last part. Well, that was fun, but what's coming up next on this channel? There's some stuff I'm currently working on. In fact, those projects are already finished, but I need to order some faceplates and do all the video shooting stuff. And one of those projects is a real dynamic spring reverb. Dynamic because it regulates the amount of reverb by your picking attack. If you don't like this feature, you can simply turn it off. And the other project is a cute little power amplifier I used for this video, but that's kept as a secret for the next episode. So if you have any questions or suggestions, put it in the comments down below. Auf Wiedersehen!